Good day everyone, my name is Graphics. In today's tutorial, we will be looking at an aspect of control system, which is the second order linear differential equation model, where we'll be solving this problem associated to it. And the question says, a second order system is described by the differential equation 5 theta sub o with double dot plus 7 theta sub o with a single dot plus 22 theta sub o with no dot equals to 22 theta sub I with no dot. Determine A, the undamped natural frequency of oscillation, B, that the transient response of the system is oscillatory, C, the underdamped frequency of oscillation, D, the time constant. Solution. The first thing that should come to your mind is for you to write the common form of the second order differential system equation. And what is the common form? It's given as theta sub O with double dot on it plus 2 times zeta, which is called the damping ratio, times omega sub n, which is called the natural frequency, times theta sub o with a single dot on it, that is the output signal, plus omega sub n square, which is we said is the natural frequency, times the output signal, which is theta sub o, equals to the g sub ss, which is the steady state gain, multiplied by the natural frequency square multiplied by the input signal, that is theta sub I, right? So what I'm making you understand is that what the theta with sub o in it means output signal, and the theta sub I means the input signal, the g sub ss means the steady state gain, and the omega sub n means the natural frequency, and the zeta here means the what? The damping ratio. Is that okay now? Now, one thing you need to still understand, I'll term this my equation 1. So what you need to understand, in your calculus, right, there's something we call second order differential equation, right? That means when your derivative is differentiated twice. When you differentiate twice, you say that what? It is a second order derivative. My y dot dot. Since you are saying the square y all over what? The x square. Because I was differentiating y with respect to what? To x. So when I have my y equals to 2x square, it will give me my dy over the x of 2x square, meaning my derivative of 2x square will be what? 4x. If I now go again, I now differentiate again, to now become the square y all over what? The x square, and that will give us what? 4. If you remember this from your calculus, your advanced calculus, this is what we have, right? Now, the first one you have here that you differentiated the first time, the first derivative is called the first order, while the second derivative that gives you 4 is called the second order. So in this case, we are differentiating with respect to what? Respect to x. But when you have theta with 2 dots on it, it means derivative of what? Of theta with respect to time, because we're talking about time response here. So we'll be having like writing this way by saying the square theta all over what? The t square. Are we together now? So instead of writing in that way, you can write it in this way too. The square theta over what? The t square. So when you see the square theta over the t square, you should know that we are saying the same thing. Now, the given equation from the question itself is given as 5 theta sub o with double dot plus 7 theta sub O with a single dot plus 22 theta sub O with no dot equals to 22 theta sub I with no dot, right? So this is what we have here. So what we'll do here is that we want to be able to compare equation 1 with this equation that is given. And one of the conditions is, if you look at the equation 1 there that we have, it has the second order here, the theta sub O with double dot on it has no what? No coefficient. So you need to make yours also have no coefficient. How will you do that? Is by dividing through by 5. So if I divide through by 5, I will say that 5 theta sub O with double dot divided by 5 plus 7 theta sub O with single dot divided by 5 plus 22 theta sub O divided by 5 equals to 22 theta sub I divided by 5. So what will I be having? I'll be having theta sub O double dot plus 7 divided by 5 is 1.4 theta sub O with single dot plus 22 divided by 5 is 4.4 theta sub O equals to 4.4 theta sub I. So I'll term that my equation 3. Now, the question you should be asking yourself, possibly asking me, is that why all this? And the reason is we want to get two important parameters. One of them in the question is the undamped natural frequency, which is given as omega sub n, and the other is to get the damping ratio, which is given as what? Zeta. That is the main aim while we are doing all this. By comparing equation 1 and equation 2, we're able to get what? The damping ratio and also what? The undamped natural frequency. So let's move. Comparing equation 1 and equation 3, if you look at the natural frequency in equation 1, right? The closest thing to it is theta sub O, right? So in terms of theta sub O, such that I'll put my equal sign. In the left hand side, my theta sub O with no dot has a quotient of what? W, so omega sub n square, which is the natural frequency. And at the left hand side of equation 3, we have the theta sub O have the quotient of what? 4.4. So what are we writing here equals to what? 4.4. Are we together? Now, by the time you do the needful, you will now take your square to the other side. My omega sub n, which is my natural frequency, is given as what? Square root of 4.4, which is given as 2.1 rad per seconds. So 2.1 rad per seconds is our undamped natural frequency of oscillation without damping. Now, for the damping ratio, we'll be comparing theta sub O with dot on it. Why? Because the quotient of theta sub O with dot on it is the damping ratio and the what? Natural frequency. So we're comparing it in equation 1 and also in equation 3. In that way, we'll be able to get our what? Our damping ratio. So let's proceed. So if I'm considering theta sub O with dot on it, such that I put my equal sign. In equation 1, what is the coefficient of theta sub O with dot on it is given as 2 zeta omega sub n. This is what we have. That is 2 times the damping ratio times the natural frequency. That is for my equation 1. Then for my equation 2, what I have as the coefficient of my theta sub O with dot on it is 1.4. So we equate each of them. So equating each of them, so we already have my my omega sub n as 2.1. So to give us 2 times zeta times 2.1 is equals to 1.4. And 2 times 2.1 will give us 4.2 multiplied by the zeta equals to what? 1.4. And we divide both sides by 4.2 our zeta will now be equals to 1.4 all over 4.2. So the zeta will now be equals to 0.334, right? That is our zeta. And the big question says that we should determine that the transient response of the system is oscillatory. So what are the cause of oscillation of the transient response? And this occur when the damping ratio is underdamped. And when is the damping ratio underdamped? When it is less than what? Less than 1, but not equals to or greater than 1. So if zeta is less than 1, we say it is what? Underdamped. If zeta is greater than 1, we say it is what? Overdamped. If zeta is equals to 1, we say it is what? Critically damped. So that is our answer there, right? So we move to the next one. The question says we should determine the underdamped frequency of oscillation. So to calculate for the underdamped frequency of oscillation, we have a general formula for it, which says that the omega sub d is equals to omega sub n multiplied by the square root of 1 minus zeta square. So if you input your parameter here, you'll be having omega sub d equals to our omega sub n, which is our natural frequency, is given as 2.1 multiplied by the square root of 1 minus zeta square. Zeta is given as 0.334 all square, which will now give us 2.1 multiplied by the square root of 0.334 square is 0.1116. So 1 minus 0.116 will give us the square root of 0.8884. And when you look for the square root of 0.8884, you'll be having 0.943. And this will now give us 2.1 multiplied by 0.943, and that is 1.98 rad per seconds. So that is what the underdamped frequency of oscillation. Now the last but not the least for this question, it says we should determine the time constant, and is represented using the symbol tau. So the time constant, recall, the time constant tau is given as what? The inverse of the natural frequency times the damping ratio. That is 1 all over natural frequency times damping ratio. 1 all over omega sub n times zeta. That is what we have as a formula. So when you input your value here, we will now be having this to be 1 all over, put the value of W sub n, which is the natural frequency, and that is 2.1, multiplied by the damping ratio zeta, which is given as 0.334, and this will give us 1 all over 0.7014. And when you look for the inverse of 0.7014, our time constant tau will give us 1.43 seconds. So this is what we have, right? So this is what we have. So you need to understand that this is how you go about for this particular question. So we'll meet in our next question. If you have found this video helpful, please don't forget to like the video, subscribe to the channel, and also share the video. Thanks for watching.